Alright, quick little video here focused on manipulating the average velocity equation to solve for different variables, and then we're going to walk through a few practice problems involving position versus time graphs just to give you guys a sense of what that looks like and some practice solving some problems. So let's refresh the equation for average velocity. We've said is average velocity equals change in position or displacement, delta x, over change in time. If any of you have been checking out your book recently, you may notice that your book likes to use d instead of x for position. Just know that those are interchangeable. So sometimes you'll see if you're checking out your book, this is a little lowercase d. But I will be using x, so get used to that. We talked a little bit previous class about how to solve for displacement, right? Change in position is also equal to the final position, x sub f, minus the initial position, x sub I, and that's basically saying that you're subtracting your starting location from your ending location, right? And then of course your change in time is the exact same thing. It's going to be the final time, t final, minus t initial, right? So if you start walking and you walk for 3 seconds, your t initial is going to be 0 seconds and your t final is going to be 3, so your delta t is 3 seconds. One pretty useful way that you can manipulate this equation to solve for some different variables is to solve for either final or initial position, right? Say that you know how fast something's moving and you know where it starts and you know how long it's moving that fast. How can you mathematically solve for where it will end up, right? So if you've got, right, this is the same equation that's written above. I've just changed our time final minus time initial back into delta t for now, right? So through some manipulations here, let's get another color going, right? I can solve for final position, right? Say I multiply by delta t, change in time, I then have average velocity times change in time equals final position minus initial position. Right, so I can solve for either my final position or my initial position from this point, depending on what I need to find out. Say I wanted to know where this object ended up. I can use x final equals average velocity change in time plus initial position, right? And it's just some basic algebra, right? To get there, I added the initial position to both sides. And this can be useful for solving simple word problems. If you look down right below here at the bottom of the page, I've started with a simple word problem here. A mouse scurrying across the kitchen floor starts, little typo there, 3 meters from my fridge and travels with a velocity of 1 meter per second for 2 seconds towards the fridge, right? At the end of the 2 seconds, how far away from the fridge is the mouse? Right, so the first step in this problem is to figure out what are they asking me for? It wants to know at the end of the 2 seconds how far away from the fridge is the mouse, right? So we're looking at the end of the time interval, right? And we want to know something about distance, right? So it's a safe bet that we're going to want to solve for final position. At least that's my initial inclination, is that we're solving for xf, right? And we can look through here and figure out what values, right, for what variables are already provided, right? We're given this value of 3 meters, right? And it says that the mouse starts at 3 meters. So this is most likely my initial position, right? We're also given the velocity, right? And the time interval, right? 2 seconds. So we have a bunch of information here. It's just a matter of plugging it into the correct spot in our equation and solving accordingly. So let's, sometimes with these word problems, I find it helpful to draw a quick picture, just so we all know what's going on. Right, so in this case, we're talking about a mouse crawling towards my fridge. Right, so if this is my fridge, use your imagination, right? And we've got a straight line, right? We're still just working on motion in one direction. There's our straight line, and here is my mouse, right? My little particle. So we know that the mouse starts three meters from the fridge. 3 meters. So I'm going to go ahead and, for the sake of simplicity, assign the origin to the fridge, right? So the fridge is going to be my origin or my 0 point. Okay, and the mouse is going to be the position 3 meters in the positive direction from the fridge. Okay, so now we have a general sense of what's going on, right? A mental picture. Let's see if we can solve this using our equation. Reminder, equations right here. X final equals velocity times time plus final, or plus initial position, right? So if my velocity, right, this is the one tricky part about these questions, it says that my velocity, the velocity of the mouse, is 1 meters per second towards the fridge, right? So the way that I've drawn this with the positive direction being over here, if the mouse is traveling towards the fridge, right, which is the negative direction, its velocity is going to be negative, right? So I have to remember to include that in my equation, that the velocity is actually -1 meters per second. So let's go ahead and try this. X final equals average velocity, which I've just said is -1 meters per second. And then our time interval, right, is time final minus time initial. Since nothing's been stated as my initial time, it's safe to assume that it's 0 seconds, so my change in time is going to be 2 seconds. The amount of time that the mouse is moving that constant velocity is 2 seconds. And it starts 3 meters away from the fridge, okay? So if we go ahead and do a little math here, -1 meters per second times 2 seconds equals -2 meters, okay, plus 3, which is our starting position. This math shows us that after those 2 seconds, that mouse has a position of 1 meter away from the fridge in the positive direction. Okay. Now you may have known that intuitively. This is a relatively simple problem with simple numbers, but as our numbers get more confusing, being able to use this problem or this equation to solve more complex problems will serve you well. So without further ado, let's check out some practice problems. Page 39 in your book is where these are from. That's in chapter 2. If you don't have your book for whatever reason, I've described them pretty much in their entirety here, so you don't really need your book. All the chapter practice problems in your book have solutions in the back of the book. So if you're ever unclear on something, want a little more practice, they're a great way to get that practice and then be able to check your answers. So what I would like you to do, this first figure here, right, this graph, applies to questions 1, 2, and 3, and this bottom one here applies to this question over here, right? So I would like you to pause the video right now and take a moment and work your way through questions 1, 2, and 3. When you've finished questions 1, 2, and 3, come on back here and I will give you my answers to the questions and you can check your work. Alright, so if you've worked your way through 1, 2, and 3, let's go ahead and talk these out for a little bit. Number 1 asks you to describe the motion of the car in the graph, right? So first thing that we're going to want to do when we describe the motion of the car is figure out where it starts, right? Where is it at time 0, and what direction is it moving in time 0, if it's moving at all, right? So I go ahead and I look at time 0, and I look all the way up to where it intersects with the line. It looks to be about 120 meters, right? So I know that the car starts, I'm just going to make little notes over here about, things that might be useful to include in my description of motion. Car starts 125 meters from the origin, and it's important to include too that it's in the positive direction, right? Positive direction, okay? Then to get a sense of what direction the car is moving from there, I want to go ahead and look at 1 second, right? After 1 second has elapsed, looks like the car is around 100 meters away, okay, from the origin. So it's moving towards the origin. And that tells me that it's moving in the negative direction, okay? So now I know where it starts and I know what direction it's moving. Another thing that you can try to determine from the graph is generally what is the velocity, right? Remember, velocity and position versus time graphs is the slope of the line. So it looks like our line has a pretty consistent slope, right? So we can tell that it's moving at a constant velocity. And that slope seems to be about 25 meters every second, right? So it seems to have a constant velocity of about 25 meters a second. I'm going to throw a negative sign in there for good measure because I know it's going in the negative direction. Therefore, its velocity must be negative, right? And that's pretty good for my, description of the car's motion, right? It starts, I could say the car starts at time 0, 125 meters from the origin in the positive direction. It's moving with a constant velocity of negative 25 meters per second in the negative direction, right? And that gives you a pretty good sense of, the motion of the car. All right, let's move on to question 2. Draw a motion map that corresponds to the graph. Okay, so motion maps, I'm going to get a nice, extend the page a little bit here, get a nice straight line going to start off my motion map. And I'm going to want to sort of give some idea of what position I'm working with on this motion map. I'm going to go ahead and put my origin actually down over here. We'll go ahead and say that's 0. And maybe 50 will be here, positive 50, 100, and 150. Right, remember to give an indication of what directions you're talking about. That's going to be my positive direction. Then we'll go ahead and have negative 50 down over here on the other side. Okay. Remember, with your motion map, each particle is 1 second. Right, so each dot I make is going to be 1 second. So this first dot here is going to be time 0. At time 0, we've said that the car is at 125 meters from the origin, positive. Okay. See if I can make my dots a little smaller. There we go. All right. Time 1, if we go up and look at our graph, after 1 second, we're at about 100 meters, and so on and so forth. Okay, so time 2, 75, 50 at about 3 seconds, so 1, 2, 3, that adds up. 4 seconds, we're at 25 meters from the origin, and then at 5 seconds, we are crossing the origin. 6 seconds, we are negative 25 meters, and finally 7 seconds, we are 50 meters on the negative side of the origin. Okay, I'm not going to put in my arrows because that's going to get pretty messy using my pen here, but as you know, you can draw arrows either halfway in between the dots or all the way, just sort of indicating what direction the particles should be moving in. There's my lame arrow. All right, so your motion map should look something like this. The big thing between this, right, is because we've said this is a constant velocity, the space between your particles should be pretty much equidistant. Okay, big takeaway there. 3, we've got some more reading of the map here. Assuming the positive direction is east and the negative direction is west, so we've got a little more information. We now know that this way is east, and down here in the negative direction is west. A little more context. A says, describe the car's motion when the car is 25 meters east of the origin. Okay, so we've just been told that east is positive, so we want to look at 25 positive. Okay, 25 positive meters, scroll on over. That's right about here. Okay, so that happens around 4 seconds. And the question is, describe the car's motion when it's 25 meters east of the origin. And it seems actually that the motion hasn't changed all that much since it left the origin, right? It's still moving at a constant velocity of negative 25 meters per second in the negative direction, okay? So we could use something similar to what we answered for question 1, right? For 3A, right? Describing the car's motion, it's moving at negative 25 meters per second at a constant velocity, okay? B, where is the car at 1 second, right? Again, just reading the graph, 1 second here, trace it up. It is 100 meters, and now that we have the concept, we can say 100 meters east of the origin. All right, so that is questions 1, 2, and 3 on page 39 of your book. So again, why don't you pause your video, take a second to check out this question down over here, that figure 2.4, again on page 39 of your book. This is the question that we're going to be looking at. Oh, hold on. There is no question. Oh, yes, there is. This one here. describe in words the motion of the two pedestrians shown in the figure, right? So we have pedestrian A, pedestrian B. This position versus time graph describes their motion. So you're going to go ahead and write down a few sentences talking about what they're doing and how they're walking. So go ahead and pause and give that a second, and then click play and we can talk about our answers. All right, so you want to start out by taking these in pieces, right? And trying to look at the motion and starting place of each pedestrian on their own, and then look at them in the context of each other, right? So we're going to take a few brief notes on each pedestrian. Let's start with pedestrian A. Okay, pedestrian A, we see at the origin, time 0, is starting west of High Street, okay? And they're moving with a positive velocity, right? They're moving towards, in the eastward direction, right? They're moving towards High Street. So we can say A starts west of High Street, moving east, okay? B is the opposite, right? They're going to start east of High Street and they're moving west, right? They're moving towards a westward position, okay? So B starts east of High. I'm just going to abbreviate this. You guys can do full sentences if you want. Moving west, okay? There aren't numbers on this graph, so probably not reasonable to try to calculate any sort of velocity, but you do get a sense of their general direction from the slopes of the line. Anytime you have two objects that you're looking at, probably a good idea to figure out what this intersection means, right, and include it in your description, right? So the intersection of this line, right, means that this is the moment when pedestrian A and pedestrian B are in the same position, right? So they have the same position here. And then you can see after this intersection, they continue on their merry way, right? Pedestrian A continues east and pedestrian B continues west. So we might want to say something about this intersection, right? So in our description, we might say the pedestrians pass slightly west of High Street. Right, they pass slightly west of High Street, right? And remember, High Street here is, in this context, our origin, right? So think about these are two streets. High Street is maybe intersecting Broad Street. Right, the pedestrians pass each other slightly west of High Street, and then they both continue walking in their respective directions, right? So if your description included any of those details, hopefully all of them, you are on the right track. Let's see, this was the answer to number 2. All right, that's all I've got for this brief video. We will work on more practice problems, including position versus time graphs, as well as velocity versus time graphs next class.